Welcome to online lesson 1, optics. So the first thing we talk about is lateral inversion. Deals with a plane mirror. Shows things the same size, but it flips right and left. And that's called lateral inversion. So your left arm appears on the same side as your left arm in the mirror image when it should be opposite sides. Okay. It's called lateral inversion. Good little definition to start your day. We'll talk about light being refracted. The speed of light depends on the material through which the light is traveling. So when light hits like water or light hits like glass, it changes speed. What happens when it changes speed is it will bend or it will refract. And so it's also affected by the density of the material through which it's traveling. The more dense it is, the more it will refract. In order for this to happen, the light must be able to penetrate the material, so it must be transparent. And that's refraction. We dealt with some of that in the lab, but we're going to deal with it in more detail because there's certain properties of light being able to refract. So here's your diagram. Where's my angle of refraction, my angle of incidence, my refracted ray, and the normal. Remember, your refracted ray comes in that's that light being sent in the beginning. The angle of incidence deals with the normal. The normal is perpendicular to the object of the whatever is being refracted, yellow glass block, and then within this is the angle of refraction right here. Note the angle of incidence is not equal to the angle of refraction. It's not the same as Snell's law, where the angle of incidence equals the angle of reflection. This is refraction, not reflection. So then your incident ray comes in, and then the ray is refracted, and the angle changes, and it goes right through. You are totally responsible for being able to label something like this on your test. No pressure. Give you some time to copy that down. So what happens to light at the air glass boundary? The light will hit the glass, it'll travel a different speed, and it'll bend. So from air to glass, the light traveling from air glass is bent towards the normal. When light enters a more dense medium, it's refracted towards the normal. This is the normal line right here, perpendicular to the object. So this tells you that angle come in. When you go from glass to air, the angle bends the other way because it speeds up. It exits the glass. Since it's not traveling through anything, it speeds up. So the angle of incidence at the air glass boundary is 0. The light ray does not deviate from a straight line path. In this particular case, the light ray appears to travel straight through the glass block. So when you shine the light straight through, coming in perpendicular, angle of incidence is 0. It will not bend. Whoa, that's crazy. This is the effect of diffraction. With the straw, it makes it look like it appears bent. The stone looks closer to the surface than the water than it really is. The light rays from the stone are refracted as they leave the water. The brain assumes the rays have traveled in a straight line and fooled to form the images right here, as opposed to where the image actually is. That's the thing that happens when you have refraction. This applies to fish too. So you see this fish inside. He's looking out through the light. He thinks the image is the prey is here, but it's actually where the prey is. But the archer fish allows the refraction of light to surface the water when aiming at the prey. The fish is a lot smarter than it looks. And so the fish does not aim at the refracted image, but he actually aims where he knows the prey is. Pretty smart fish. And this is what happens with refraction. The fish appears closer than it really is. Total internal reflection, as you shine the light into the ray, you might have seen this happen. When the angle of incidence is too big, the refracted ray disappears and the incident ray is reflected back inward. This is called total internal reflection, not refraction, because it does not go through the surface. So in total internal reflection, the incident angle is too big, the refracted ray disappears, and the incident ray is totally reflected back inside the glass block. This is how fiber optics work. How many of you have true fiber optics? They're sending like a laser with data on it, and the way it works is you have this optical wires, they're glass strands put together, and the lights guide through the cable by successive internal reflections. That's why you can't put a bend in that cable. Like I have a router for true gigabyte internal like optic fiber, and I bent it once and I broke the thing because you can't have a bend at all. It has to be pretty straight, or the internal reflection doesn't work anymore. Therefore, your data won't travel, and therefore they have to come and fix it, and they'll give that funny look like, "Don't you know you're not supposed to bend it?" Whatever.